Recently, Xu Lewong telling us about the latest models that realize Xeon one-phone symmetry for topological states for M. And let's welcome Lewong.
Thank you very much for choosing for the kind invitation to talk about this work. Shout out. Just want to mention that the slide for this work is available on the website down below. So if you're interested, you could take a look at it. Go ahead. So let me jump into the preamble. So I'm studying topological phases, which are gap phases of matter that despite sharing the same symmetry, they must undergo some gap closing transition to reach another phase. And I'll be focusing on two major groups of topological phases. The first one is topological order, which has degenerate ground state on closed manifolds with a non-trivial topology. And the other is SPT, which has unique ground state on closed manifold and can be deformed into the direct product state written as follows. By deform, I mean local unitary transformation. And the trivial SPT can be deformed into the direct product state while preserving the symmetry. And non-trivial SPT, which is not the trivial SPT, is characterized by its boundary, which cannot be uniquely gapped in all spatial manifolds. And this boundary is typically gapless or spontaneously breaks symmetry. Sometimes it will develop topological order. And we could view this property as being protected by an anomalous symmetry, which is encoded into anomaly. So by symmetry here, we traditionally mean a symmetry that acts globally on the entire space. But in this talk, we're focusing on higher symmetry, which means that the symmetry is acting on the lower dimensional subspace. And to be clear, we are restricting ourselves to bosonic systems where the symmetry is on-site, so no spatial symmetries. It's unitary, so no time reversal. It's abelian and also finite. It's my native flavor higher symmetry. So to give some motivation of why...
Should the higher symmetry act locally on like links or simplex or still on site?
On links. So not necessarily on the site, but I'll get to that later. Thank you for the question. So to motivate why we study a higher SPT, let's consider an example where we will see the higher SPT, but the high symmetry actually arises from some emergence. So consider this Hamiltonian on a 3D cubic lattice with a C2 variable defined on the length. So each length now carries a variable +1 or -1. And the Hamiltonian has two terms. The first term is summing over all the plaquettes in the spherical, in the cubic lattice. And for each plaquette, we multiply the 4 lengths in the plaquette for the sigma z variables. And for the second term, we sum over all the sides. And for each side, there are 6 outgoing lengths. And for each outgoing length, we product them together. We take the product of the sigma x of those lengths together. So you see that these two terms actually commute with each other, and it's the 3-dimensional analog of the toric model, and it has a topological order ground state. So if you define it on 3 torus, there would be 8 degenerate ground states which are labeled by this quantum number product over C on a non-contractible loop along the 3 cycles of the 3 torus. And this variable could be plus or minus that labels individual ground state. So the excitations of this toric model are the following. So if you violate the star term here, then this would give you a point charge. So meaning that there will be some location where if you product this 6 lengths outgoing on an individual side, it gives you a -1. That's a point charge. And if you violate the first term here, meaning that say, if you imagine there is a line I call C twiddle that runs through a number of plaquettes, and along the plaquettes which are perpendicular to this C twiddle line, the product of plaquettes of C is -1. That gives you a line excitation, so you would give an excitation that lives on lines. So, this model is exactly solvable, but we could consider adding 2 terms, a TC and a BX. Its meaning is the following. So if these 2 terms are much smaller than the first two terms, what we said before still holds. But this T, which is summing over C operators on individual lengths, actually hops point charges. So if you add this C operator on a location with a point charge, it would make the excitation of the point charge move by one lattice spacing. And this B operator is a hopping operator for the line fluxes. So if you add this X operator on a particular line that belongs to a plaquette where this product C is being violated, then it would perturb the loop to move over. So it's changing the line flux configuration. Now, if we consider the special case where this T is much smaller than the rest of the three, that means that we are immobilizing the point charges. So the point charges just sit in place, they cannot move around. And as a result, if you enclose any charge in any closed surface, the enclosed charge is going to be a conserved quantity. And a conserved quantity will give you some symmetry. In this case, it would be an emergent symmetry, which the generator can be written as the following. If you take the product of the X lengths, which are intercepting the S twiddle closed surface, then it would be a generator for a symmetry, which is supported on a surface, which is a codimension 1 manifold in this case. And this operator computes with Hamiltonian, except with the T term, which we assume to be very small. So this is an example of a K symmetry where K equal to 1. So K is the codimension on which the symmetry acts. And the traditional global symmetry, which acts on the entire space, corresponds to K equals 0. So codimension 0 means the entire spatial manifold.
So that's a very neat question. So Z I live on things, right?
In this case, yeah, C2 lives on the length of the cubic lattice.
But you have Z and X.
C and X. Sorry, what do you mean by C and X?
You have Z, Zi, and Xi.
Oh, ZL, L. So L is the
L.
length. These are all on lengths. L is
X also live on things.
Yes. So I means site. So when I say L belongs to a star, I mean particular site.
One is like fully X, one is like fully Z, 2 by 2 matrix.
The L corresponds to the 6 lengths connecting to I.
Yes.
I think you try to ask
So Z2
what they are.
what's the meaning of these variables?
C2
Fully
variables
plus minus 1 values, right?
Yes, on each length there is a plus or minus 1.
So you have two variables.
It has two values on each length.
But Z and X, they are all allowed to. So they're labeled by the same thing as they're independent.
One is
No,
fully
no,
X,
they
one is
don't
fully X, fully Z, 2 by 2.
C means
Sigma X, sigma 2 by 2. Fully matrix.
a minus 1 acting on a length. This means
Oh, okay.
poly
Yes,
acting on a length. Thank you for the question. Okay. So let me give an overview of my talk. So just as those zero symmetries protect neutral SDTs, actually these K symmetries also protect higher SDTs, which are called K SDTs. And in my talk, I will be focusing on building a lattice model for realizing 3+1D or 3 spatial dimension 1 SPTs that have K equal to 1. This one symmetry will be supported on membranes. And my symmetry group is Zn with n even. And I will denote my spatial manifold as a regular M subscript 3 and space-time manifold as a curly M superscript 4. So if my spatial manifold has a non-empty boundary, so in this case my spatial manifold is a box, it has a boundary that is the top of the box, then the one symmetry operator S twiddle may end on the boundary as string operators. So in this case, there is a hemisphere which represents this S twiddle on which the one symmetry lives, and this ends on the top of the box as a string. Just as in the zero symmetry case where the boundary symmetry can be anomalous, actually in our case, these string operators can also be anomalous. And I will show you later on that this string operator corresponds to a hopping operator for non-trivial anyons. We also show that the bulk ground state wave function in this case has a geometric interpretation. So it's actually related to the linking number of the flux length. I'll show you that. So disclaimer is that this lattice model, I'm not the first guy to study it. Actually, referenced by Wang, Zhifen, and Zhang study it in the Lagrangian formalism as well as Xiaogang. But here I will be using the Hamiltonian formalism, and I write down the symmetry operators explicitly. This is a table of contents of my talk. I'll be doing a background review. I understand that people here are experts on the subject, but because once I put the zero symmetry reviews in a particular framework, it's actually very trivial to generalize it to a higher SVD case. So I'll just do a slight review here. And then I'll give two arguments for the anomalous boundary strings, and informal heuristic argument, and also a more formal argument. After I establish that, I'll test with building some boundary Hamiltonians and seeing whether they obey the prediction, namely that there is some emergent anions. Finally, I'll talk about the safe wavefunction interpretation. So let me quickly go through the zero sim SPT review. So I will use capital D to denote the space-time dimension, small d to denote the spatial dimension. I assume my space-time is triangulated, and its action, its partition function is given in this form. So I'm summing over all the A0 of this quantity, integral of md over the cocycle omega d. So I'm using the cocycle classification, and I assume that omega d belongs to the cohomology group of BG U1. Here, A sub 0 is a variable living on site. In general, A superscript n is a G-value n cochain, so it's assigning a group element G for any n-dimensional simplex. In our case, the zero-dimensional simplex is a point, so it's associating a group element to each point, and each simplex is denoted by its vertices from I0 to In, and I will denote the group operation by addition. So a heuristic way to view this field is that when you have n equals 0 because A0 corresponds to a scalar field living on site. A1 would probably correspond to a vector field that has 3 components roughly. And the symmetry in this case is that if we change A0 in the action by adding an alpha term, alpha 0, which is also a zero cochain, so it's also assigned a group element to every site. So we further require that d of alpha 0 is 0. So d here is the co-boundary operator. Usually people denote it by a delta operator, but for me I use d. D alpha 0 equals 0 means that alpha is a uniform function on connected components. So this statement means that I would shift A by the same value on every connected component, which is what the global symmetry means usually. In general, we can also consider a B hat here, which is one cochain or one form that represents the background gauge field. So obeying dB1 equals 0, sorry, there should be a D here. But in this talk, I'll just neglect it and choose the 0 background flux. You could not neglect it, but I'm not doing that here. Any questions?
Okay, so what's the meaning of omega d bracket b?
So omega is a cocycle that depends on the link variables or the site variables. So omega d in this case means that if I have a d simplex and I'm given, say, some link configuration, in this case dA0, so I have dA0 on every link specified. Then omega would take in such a configuration and outputs a number for me. And belongs to this cohomology group. Means that it's only defined modulo 1. It gives me a number modulo 1. It satisfies some conditions. Say, cohomology group means that d omega need to be 0, for example. It's a particular set of functions defined on the configuration, satisfying some conditions.
What do you try to emphasize in the last sentence of the previous?
So this is saying that I could study SPT with a non-zero background gauge field. So actually, I could have a twisted spatial boundary condition. I could study SPT on those cases, but I'm not doing it here.
But what you say isn't that the same thing to repeat twice? You mean that the obeying DB is 0?
I should have D here. This is a typo, sorry. DB1 equals 0. So once we know how to write down the action, there is actually a very standard way to derive a exactly solvable Hamiltonian and derive Brown's wave function. So I'll give a review here because it can be straightforwardly generalized to the k-equivalent case. So imagine we have a cocycle fixed, and we could write down exactly solvable Hamiltonian, which I call H infinity, which has a Hilbert space, a tensor product over every side of A0 of I. So if there are n sides in the spatial manifold, then the dimension of this Hamiltonian would be order G to the power n. So the transfer matrix can be defined in the following. Transfer matrix element that takes a side configuration A0 to a side configuration A prime 0 is proportional up to a volume dependent term to this phase here. So this phase here involves an integral over the space-time manifold np times interval I of this cocycle of the dA0 configuration. So you could think of it as this cylinder here, where the spatial manifold np is represented as a circle. And what we could show for this case is that this operator, once you define the Cauchy element as follows, it's a projection operator, meaning it squares with itself, and its trace is also equal to 1. That means that its eigenvalue is either 1 or 0, and there is only one eigenvector with eigenvalue 1. So the energy for this Hamiltonian is 0 for that unique ground state, otherwise it's infinity. And for that unique ground state, actually we could construct another Hamiltonian that shares the same unique ground state as this H infinity Hamiltonian. So this Hamiltonian without the H subscript is defined by the following. It's sum over all the sides I of the P operator, which is depending on the side I. So each PI operator are projector operators which has a matrix element that involves a diagram as follows. So if we try to update the side I to we'll try to update the configuration A on side I to a configuration A prime of side I. And in 1D is denoted by this figure. In D equal to 2, it would look like a small tent updating a side I to a side I prime. This figure was stolen in this paper. So I want to show that because of a condition we impose on cocycles, these figures are invariant under retriangulation. So meaning that you could redraw the arrows within the interior of this diagram without changing the value of the projection operator. And this would imply that this PI will be commuting operators. So if neighboring PI and PJ operators act on PJ followed by PI, then you could redraw the figure so that the arrow, so this first update side J and then update side I, you could redraw the arrow so that it's the same as the figure where you first update side I and then you update side J, which is acting PJ, PI in opposite directions. And in D equal to 2, you could do the same thing. It all comes down, it's all originating from this equation, D only equal to 0. If you have two small 10 operators, then acting one before another is the same as acting J and then up and then act I. So once you have the Hamiltonian, you could discuss this ground state wave function. Say, suppose your spatial manifold MD is the boundary of the space-time manifold curly MD, and the bulk of the space-time is can be represented by a single site 0 star, and the ground state wave function for the Hamiltonian written before is actually proportional to the volume dependent term to this quantity of integral over this space-time with a boundary of the cocycle omega d. So for example, in spatial one dimension, this space-time wave function is represented by this figure, where the top of the space-time is denoted by a zero-star vertex, and this disk, when you evaluate the cocycle on this disk, it will give you the wave function on the 1D ring. And in the two-dimensional spatial case, if you have a zero-star vertex that is in the top of the space-time, and if you evaluate this omega d on this open manifold, which is a ball, and it will give you the wave function depending on the surface, which is a sphere. So the important point here is that to obtain the ground state wave function, we solve the following equation. Namely, we set omega d of dA equals to d of something. That's something I call phi d. Then by Stokes' law, it would be easy to see that the wave function can be reduced into an integral over only the spatial manifold of this phi d. So the lesson here is that phi d equals the ground state wave function. For example, in spatial dimension 2 for the C2 protected zero SPT, the spatial wave function has the meaning of -1 to the power of the number of domain modes. So once we have the spatial wave function, we could consider what happens on an open spatial manifold. So we know that a non-trivial bulk SPT corresponds to an anomalous boundary transformation, and there is a procedure to read off what anomalous boundary transformation that is. So imagine if you have a spatial manifold which has a non-zero boundary, then we could define a boundary space, which is a subspace of your Hilbert space, in which this boundary degree of freedom are fixed, but the boundary degree of freedom are summed greater by the ground state amplitude. So it's given by the following formula. Roughly, you can think of it as the ground state with a fixed boundary condition. You fix the variables on the boundary of the spatial manifold. And if you perform a symmetry operation on this boundary states, due to the coupling between so this boundary state only depends on the boundary variables, which I denote by A boundary, where the bulk variables are all summed over. Due to the coupling between the bulk variable and the boundary variable, and you perform a symmetry, the boundary states actually pick up a non-onside phase that is given by the following. So delta alpha means that you change the spatial wave function, the configuration A, by alpha. So if you evaluate change in the spatial wave function, that gives you the non-onside phase. And it's the non-onside phase which encodes the anomalous symmetry. So if this change in the spatial wave function can be written as the total derivative of some other function, which I call phi d minus 1 sub alpha, so some function phi d minus 1, then again we could use the Stokes theorem to rewrite the non-onside phase as an integral over the boundary of the spatial manifold of this phi alpha d minus 1. And actually, this phi d minus 1 could be pictorially understood as the figure here, where the lower part represents the ground state wave function, which originates from the zero-star virtual vertex, and the upper part represents the modified spatial wave function, which I denote by vertex A star. So the lesson here is that by solving this equation, I will obtain a function that encodes the non-onside phase, which is the symmetry anomaly. So once I know how the symmetry act anomalously on the boundary, then I try to write down Hamiltonians, local Hamiltonians, which are symmetric with respect to those anomalous boundary symmetries, and I could study what kind of state that boundary has. So there's an example here, but I think I'm going to skip it for now. So in the remainder of this talk, I'll go to higher SPTs. And this higher SPT differs from the zero SPT actually by a small change. We could simply change the variables A, which originally lives on site A sub 0, A superscript 0, to A superscript K, where A now lives on dimension K synthesis. And I could write down the SPT partition function just as before. So here, the physical variables A superscript k enjoys a symmetry that changes each ak to ak plus alpha k. And here, d alpha k must be 0. So if you plug in this change into action here, because of this d operator here, it will have no effect in action. So it's a symmetry. And again, I could have a background gauge field that satisfies the sadness condition, but I'll be choosing it to be 0, so don't worry about that. So for concreteness, let me focus on k equal to 1. In the k equal to 1 case, A will live on length, and the cocycle omega d actually belongs to a cohomology group HD of B2GU1. And here, B2G is a space that has a non-trivial pi 2 such as it's equal to G and is trivial for everything else. And actually, this is the main reason I'm restricted to a abelian G, because pi 2 is an abelian group. So if you want to generalize this to non-abelian groups, that would be some tricks. There are some literature works for computation of this cohomology group HD of B2G, and there's also a more complete classification by looking at the coordination group by these people. So let me argue why the one symmetry acting on membranes. So for a given d-dimensional simplex, d-dimensional lattice MD, we could construct the dual lattice by relating the k simplices in the original lattice, which are denoted black in this case, to d minus k cells in the dual lattice, which are denoted red. So for example, here, a 2 simplex triangle is due to a 0 cell point here, and a 0 simplex, which is a point here, is due to a 2 cell, which is a hexagonal here. And under this duality, this k cochain would be due to a collection of d minus k cells in the dual lattice and d twiddle. So the one symmetry we mentioned earlier, namely the alpha 1, which d is equal to 0 in this duality, would be due to alpha 2 twiddle. So if this alpha 1 is non-trivial on a particular link, then it would be due to alpha twiddle, which is, has a non-zero coefficient on this 2 cell. And the condition that d alpha 1 is 0 would translate into the fact that the 2 cells here has no boundary within the bulk. So that means that the one symmetry can actually be written as being supported on a membrane alpha twiddle 2 that lives in the dual lattice, and it would not end in the bulk. So at most it could end on the boundary. The one symmetry acts on length intersecting is 2-dimensional manifold alpha twiddle, and this 2-dimensional manifold could intersect the boundary as the boundary transformation shrinks. So the plan is the following. We will take group G, Cn, restrict to spatial dimension D, and we will look up from the literature for this classification of the cohomology group. It turns out that the answer is that if n is even, the one SVTs are classified by C2n numeric. If n is odd, then it would be classified by Cn numeric. And then we'll also look up the explicit formula for the omega 4 from the literature. So how to write down this function? Just look it up. And we'll write down the transfer matrix as before. And we'll solve omega 4 equals to d of something, where something is 5,3 that encodes the ground wave function. And then we'll pick a particular triangulation for the 3-dimensional spatial manifold R3. Write down the projected Hamiltonians. And then we'll solve this equation. If we change the spatial wave function by some alpha, we try to write it as the total derivative d of some function phi 2, and we could read off the boundary transformation phase phi 2 and write down the boundary transformation strings. Once we get that, we could compute linear statistics. So it's what we are going to do very soon. But before diving into that, we need to ask ourselves what we expect for the answer. So I'll present a heuristic informal argument that is not meant to be rigorous by following. So one way to understand the anomalous symmetry, boundary symmetry, is from the point of view of the symmetry fractionalization. So roughly it means the following: if the symmetry is acting on the entire boundary of some spatial manifold MD in such a way that the symmetry can be extended into the bulk, then this symmetry is represented linearly. For example, in D equal to 1, if you have a line segment, and if the same symmetry G acts on both ends of this one-dimensional SPT, in this case it's an AKRT chain, on either end it will be represented by some representation R on the right and R on the left respectively. But we know that if you tensor R on the right and R on the left together, it will be a linear representation of G, meaning that if you have the same G group element acting on both ends, then the representation is linear. But if you just restrict yourself to one end, if you just add G on, say, R sub R on the right, then the group representation would be spoiled. The linearity of the group representation would be spoiled by a phase omega 2 that encodes the two anomaly. So we expect the same lesson to hold in the 1STT case. So if we have a sudden 1STT, if we have a sudden one symmetry transformation on the boundary that can be extended into the bulk, then we expect the group representation to be linear. And if we try to restrict ourselves to a local region on the boundary, then some structure of the group representation might be spoiled. That's what roughly we expect. So let's consider the following. Suppose I have a two-dimensional boundary, and on this boundary, I have anomalous one symmetry transformations represented by these two loops Q1 and Q2. Q1 and Q2 are Cn variables denoting the strength of this one symmetry operator, and the orientation is denoted by arrow. Since each loop can be extended into the bulk as a hemisphere, we know that inside the bulk, the one symmetry is on-site, so there's no non-on-site phases. We will expect these two loop operators to commute on the boundary. So if you add Q2 loop followed by Q1 loop, it should be the same answer as if you add Q1 loop followed by Q2 loop. But if we just look at a particular small region here, where there's a crossing between the two lines, it's reasonable to expect that this commutativity between the two figures might be spoiled by some phase, which I just denoted by theta Q1, Q2. And on the other hand, if you have the special situation where both Q1 and Q2 are equal to Q, and we could have this relation that if we add a loop Q followed by another loop Q, is the same as adding the two loops in this deformed fashion. The reason is that if you look inside the bulk, these two hemispheres will intersect on an arc. But if both Q's are the same, then the one symmetry actually acts trivially on that arc where the two hemispheres intersect. And you could remove that one symmetry by reconnecting the surface of the two hemispheres so that they become two non-intersecting spherical-like membrane that ends on the boundary as follows. So again, if we look at the local region, we might expect that the equivalence between these two diagrams might be spoiled by a phase which I call theta Q. So in this small region, the diagram with the crossing might differ from the diagram without crossing by some phase. This equality tells me that the phase relating the crossing with positive crossing with zero crossing, this phase must be negative, or the phase relating the negative crossing with the zero crossing. And by comparison with the previous slide, where Q1, Q2 might not be the same, we see that theta and Q1, Q are the same. It's equal to 2 times theta Q, because the right-hand side of this figure is different by the right-hand. The left-hand side of this figure differs by the right-hand side of this figure by 2 theta Q.
What is the one and the equals?
This one means that it's modulo 1, because theta appears on top of exponential, so I allow it to differ by some integer not equal. Thank you for catching that. So you could try to argue what would this theta Q1, Q2, and theta Q look like. Let's say, suppose that this theta Q1, Q2 is proportional, is bilinear in both Q1 and Q2, and we expect this theta Q1, Q2 to be invariant mod 1 under the change Q1 by n. And it means that the coefficient of proportionality appearing here must be n bar over n for some integer n bar belonging to n minus 1. And further, if we suppose that the theta Q mentioned earlier is also proportional to square of Q, proportionality constant C, then by this relation 2 theta Q equal to theta Q cube, theta Q equal to 1, we will have 2C here equals to n bar over n up to some integer offset. So that means C is equal to n over 2n for some integer that belongs to 0 up to 2n minus 1, where this n here is the same as n bar modulo n. So by putting this m into the equations, we have theta q equals to m over 2n q squared, and theta q1 q2 equals to m over n of q1 q2. And we also expect that theta q should be invariant when we change q by n. But if you look at this formula, when q increased by n, theta q actually increased by n times m over 2 on 1. So in order for theta q to be invariant, actually not all values of m are valid. So when n is odd, then we can only allow even m's, so that n times m divided by 2 will give you an integer value. It gives you a following table. If n is even, then m could be anyone from 0 to 2n minus 1. That agrees with the C2n classification I mentioned before. And if n is odd, then this integer n must be even. That goes from 0 to 4 to 2n minus 2. It also gives you the right classification. So the summary is the following. The one symmetry operator, we expect them to obey the following relation. If you change the crossing from a positive crossing to a negative crossing, it will differ by a phase that is m over n q1 q2. And when you change the crossing from a positive crossing to a zero crossing, it will differ by a phase m over 2n q squared. What it means on the boundary is that if you try to write a Hamiltonian on the boundary, this is predicting this boundary Hamiltonian should have some emergent anions whose hopping operators are represented by these one symmetry operators. And the phases here means that the anions have non-trivial statistics. Usual statistics denoted here and statistics denoted by this. So I'll go into a more formal argument in the following. So now we look up in the literature and we write down the classification for the cohomology group or B2Cn, where n is even. And we write down the explicit formula for the cocycle. So omega 4 that depends on the configuration dA has the following form. It's labeled by m over 2n multiplied by a Steenrod square operator. So here A is a Cn value 1 form that lives on the length. M is an integer running from 0 to 2n minus 1 that gives you the classification. Steenrod square operator is some operator that takes two form or two cochain, in this case BA, gives you a 4 form or 4 cochain that is evaluated on the 4-dimensional space-time. This definition could be looked up from the appendix, so it's not very important here.
I know you just mean the ordinary square, but the Steenrod square is not defined for odd n. It's different operations.
Odd n.
Steenrod square is for even, is for n equals 2.
Yes, for n equals to 2. I think for odd n, the cocycle is still Steenrod square.
For this, it's just the ordinary square, but there's no reason to bring up the Steenrod square. But anyway, it's wrong to say for n not equal to 2. But these different like p power operations.
Not sure about.
basically just dA squared.
Yes.
For n equal to odd, it's just dA squared. Yeah, I think that.
So for n even, the formula should have this Pontryagin square.
So by Stigmar squared, it's not just dA squared. There's
No, Stigmar square 2 on 2 cocycles is just the square.
So for my definition, it's not just like that.
Yeah, but if you want to use the word Steenrod square, this is what it means.
Okay. So I don't mean the Stigmar square that you meant. Stigmar square, I mean.
It's not what I mean, it's what mathematicians have meant for 50 years. Okay.
Yeah. Okay. So the definition is different from the mathematician's definition. It could be learned from the appendix. Its exact form is not important here. I agree with
But
that.
you also mentioned Pontryagin square. Could they Pontryagin square?
There's supposed to be Pontryagin square here. This formula is just misleading.
I see. Yeah, so maybe to be rigorous to mathematician, I should replace this by Pontryagin squares, not the Stigmar square. The investment that I agree.
This may be Xiaogang's notation.
Yeah, this one is
I wouldn't recommend that.
Sorry about that. Sorry. So I should go on. Okay, so I would pick the triangulation as follows. I will have a cubic lattice in a three-dimensional space, and each cube I divide into 6 tetrahedrons. And each tetrahedron has 4 vertices, and these 4 vertices are labeled by 0, which labels the base of this cube. And alpha, beta, gamma is a permutation of x, y, z. So I will go from 0 to this 1, 1, 1 vertex by 6 different paths depending on the permutation. Each path gives me a tetrahedron. So if I go x first, and then y second, and then z third, I will have this tetrahedron. So, there are 3 types of links in my triangulation. I call it one diagonal, meaning that they connect some vertex to another vertex that differs by 1 unit vector. 2 diagonal means that it differs by 2 head vectors. 3 diagonal means that it connects from 0 to 1, 1, 1. And I could do what I did before, namely write down a transfer matrix and construct the exactly solvable Hamiltonian from omega 4. In our case, the Hilbert space is defined by a tensor product over all the links. On each link, there is a superscript 1 variable, and this A1 is takes value from 0 to n minus 1. It's a Cn variable. And we have 0 background gauge field. You can write down the transfer matrix for this projected Hamiltonian. It has the matrix element, which is obtained by evaluating this cocycle on a manifold MD times interval I, again represented by this diagram. The circle here represents a 3-dimensional closed manifold. As before, this operator can be shown to be a projection, and it has a unique ground state. For the ground state wave function, we could take the formula for omega 4, which is a contraction square, and solve this formula, set it equal to d of phi 3, and the result is the following expression. And we will return to unpack what this means later. So, as before, we could write down a Hamiltonian that has a finite energy gap by taking over the sum of local projection operators P that depends on the length L. And each PL has a matrix element defined in the following. So if you will only update one length, so you will only change AL to AL prime. If any other AL are different, then the matrix element is 0. For the configuration which change only one link, the matrix element is given by some normalization times evaluating cocycle on the manifold R3. In this case, my spatial manifold is R3 times interval. And rewrite this expression for the integral of cocycles in terms of the ground wave function stated before. It's simply it's the change of the ground wave function when you change AL to AL prime. So the result is the following. If you have even M, and it turns out on the 2 and 3 diagonal links, they just form direct product states, and we can forget about them. We focus on one diagonal link, so all the orthogonal links. The Hamiltonian is the following. You sum over all the links, and for each link, you will have an X operator acting on the link, accompanied by 2 plaquette operators F, which slightly shares a corner with the original link L, and the face of this plaquette, the center of the face of this plaquette is the center of this link plus 1/2, 1/2, 1/2. So I would call this the upper plaquette. The center of this plaquette differs by the center of this link by -1/2 length, -1/2, -1/2. So I call this the lower plaquette. F here is a plaquette operator that products over the 4 links in this plaquette of this expression. So for simplicity, let's think about when n equals to 2. When n equals to 2, this F is just product over C on this plaquette. And this X is just updating a link variable. It's quite easy to check that this is a commuting Hamiltonian, meaning that if you take any 2 terms, you will commute. So if you take this term, if this L is living on this link, there will be a -1 if n equals 2 from the anti-computation between this link and XL, and a -1 from the anti-computation between this link and this X. So they're actually commuting operators. And this Hamiltonian also enjoys the one symmetry. So if you have any closed surface that cuts a number of links, and you try to add an X operator on those links, you would commute with this Hamiltonian. For the odd n case, the expressions are more complicated. So previously we have even n, so we only care about this term. Turns out that when we have odd n, we have a lot more terms due to this troublemaker, and I'm not saying much on its expressions. I just want to tell you that it can be done. I'm not sure how to make sense of them. So we could try to see what boundary transformations we could get from this ground state wave function by again defining the boundary states as follows: summing over the bulk lengths, fixing the boundary lengths, which makes up a non-onside phase under a one symmetry operation, and that non-onside phase is encoded by this phase, which is related to the change of the ground state wave function. And to extract the non-onside phase, we could solve the equation that the change of the ground state wave function equals to d of some function across phi 2 of alpha. It turns out that we can only get a solution if I assume alpha equals to dh. We return to this point later on in the talk. The result is that phi 2 with alpha equal to dh can be written down as this form. So it's not a pretty equation, but you could still use it to explicitly write down the symmetry operators. For some insight, let's try to focus on even m. And m is even, and the coefficients here are integers. And I could forget about all these red terms. So I just focus on the first term here. The first term essentially tells you that if you change a link, and there's an accompanying A string that is attached to the one symmetry you are acting. So for example, in n equal to 2, this term, the coefficient 1 over 2, attaches a z string to an x string. So if the one symmetry operator tries to change lengths along this path, then this term tells you that you must attach a phase that essentially is a C loop that runs in the original lattice and almost closely follows the next path. So this one symmetry operator is essentially a flux loop attached with a charge loop, which we know that is a fermion in the toric. So once we have the expression for the boundary transformation, we explicitly compute this theta q and theta q1, q2. We imagine the following setup where we have a boundary, which is so we have a three-dimensional space. We make a cut along the xy plane as a boundary, a two-dimensional boundary with triangulation shown as follows. And on this boundary, we could carry out several different non-symmetry operators. So this yellow square could be replaced by any one of these squares shown below. For example, if you replace it by this W1 square, it means the one symmetry operator acts horizontally to go through this fashion. And if you act by W2, the one symmetry acts vertically in this fashion. The red region here essentially tells you what is the configuration for H I choose so that the one symmetry alpha is VH. So to extract those faces, theta q and theta q1, q2, I look at these two diagrams, which tells me that if I add the one symmetries in a certain order, the result should differ by a phase that tells me what is theta 1, theta 2. So I take, say, this figure, tells me if I add first W2 and then followed by W1, I should differ by the result W3 followed by W4, which is acting this quaternion by a phase e to the 2i theta q. And so same for the mutual statistics. If I add Q1, W1, W2 in different orders, I should expect a phase. So once you put in the previous expression and do the calculation, we found that the answer is theta q equals to m over n q squared, which at least what we expect. Theta q1, q2 is m over n q1, q2. So,
Excuse me.
Yeah.
Just make sure. So you consider 3 plus 1
boundary.
the boundary is 2 plus 1. 3 plus 1 bulk higher 1 from symmetry SP. And because right now you are writing the maybe cubic lattice and square lattice, cubic lattice in the bulk, square lattice on boundary. Well, usually when you write as Ryan mentioned, this maybe some forms for combinations where PB, it may be easier to write simplicial complex, which is typically draw. And so right now you write in the cubic lattice. So did you maybe cut down cubic lattice into several simplex and then
use those syntheses to evaluate the boundary and square.
Okay.
In this case also.
Okay. So you in the end you boil down to some triangle, 2 simplex,
Yes.
3, and then also 3 simplex, 4 simplex type terms.
Right.
Okay.
So if you look at the result and put in n equals to 2, q equal to 1, in the case where if you take the generator of the 1SPT, you get a semion for this statistics. And in the case when we take twice of the generator, we get a fermion. So this is saying that I would expect an emergent semion on the boundary of the generator of the 1SPT. I expect an emergent fermion on the boundary of twice the generator of the 1SPT. I mentioned that the same calculation can be done for any other finite abelian group G. We wrote out a formula that it can be done. So let me test what I told you with the boundary gap Hamiltonians. So I would present 2 approaches. The first approach is explicitly writing down symmetric Hamiltonian that has 2 terms. So this boundary Hamiltonian, the first term is W circle I. This W circle I is actually a one symmetry operator that acts on a small loop enclosing only one side. Since I know how to write down the anomalous boundary symmetry, I could write down this operator explicitly. The second term is a conical delta function that tries to enforce the flux on each plaquette to be 0 on this boundary. So this is a 2-dimensional boundary. This term essentially tries to set the C2 flux on each plaquette to be an even number. So I'm focusing on n equal to 2 here. By construction, this Hamiltonian is symmetric under the anomalous one symmetry, and it's also exactly solvable. And let me write down the type explicitly for n equal to 2. This W operator is product over, involve two loops. It's a product over C on this loop, so the site is at this corner I here. Also involves a loop of X surrounding this I. And if you think about the ground state, if we have the no flux rule satisfied, that means the C loop is always 1. So this operator in that subspace of Hilbert space, which is no flux, is the same as the star term in the torical. So this Hamiltonian will have the same ground state as the torical Hamiltonian. And we know that there is a emergent fermion in torical, so this is a check. For n equal to 1, we could write down the formula for W circle I, which has this form. But if we focus it on the low flux sector, then we could drop most of the terms. So any place you see dA is essentially 0. And you're only left with this term here, which involves 6 pairs of sites J and J prime, which runs through the 6 lengths surrounding the site I. So J and J prime would be 1, 6, 6, 5, 5, 4, 1, 2, 2, 3, and 3, 4. Actually, this updating term is the same as the updating term for the exactly solvable Hamiltonian you would construct for double semion models. So you know the double semion model by its name has a semion, so it's a check that there is an emergent semion. So in both cases, we develop topological order in this two-dimensional boundary, and it's actually this analogous to spontaneous one-symmetry breaking, because the one-symmetry acts non-trivially on the ground state manifold. And actually, there are many ways to write down a boundary Hamiltonian here. We're essentially trying to suppress the flux here. Suppressing flux in the one-symmetry case is analogous in the zero-symmetry case to suppressing domain walls. So it would be reasonable to expect to suppress domain walls in a zero-symmetry boundary, you would have spontaneous zero-symmetry breaking as well. I also mentioned that this W circle I operator in the n equal to 2 case, they are actually related to some constraint in the exact2D polarization paper by UN Kapelstam and Fish, which is an interesting connection. So the second approach we're going to do is the Lagrangian approach. So we take the form of the ground state wavefunction before, and now instead of interpret it as a spatial ground state wavefunction, we interpret it as the y-Symmetry term on a 2 plus 1 dimensional space-time of the boundary. So if we interpret this as the y-Symmetry term, and we enforce the low flux condition by hand, and this phi 3 would reduce into the following term because dA is 0, so we could forget about this extra term here. And we could also put a factor of 2 from the denominator into here. And it's a technical comment that when dA equal to 0, actually the quantity here, dA over 2 is the same as A cup A. So I omit the cup symbol because both of them only give a non-zero answer evaluated on this triangle 0, 1, 1. So we express the y-Symmetry term on the boundary as L over 2 to A cup A, which we recognize is actually the topological term for the double semion model. And when n equal to 1, so that the coefficient is 1/2, that's the topological term for the double semion model. When n equal to 0, this is an integer, so we can forget about that. It just gives you a C2 gauge theory. So we expect there is a connection between the boundary of the one SKT to the double semion model when n equal to 1. We suppress all the terms. I mentioned that there is a more general approach for getting a gap boundary of higher STTs, which using higher symmetry extensions. It's work by Lokman and others, several works. think they also expect emergent fermions, semions for the n equal to 2 and n equal to 1 SPD in our case. So lastly, let me go to the geometrical integration for the ground-theory function. So remember that we have written down the ground-theory function. And for simplicity, let me assume m is even, so I only care about a cup dA term here. And let me try to unpack what this means. Under Poincare duality, one cochain A is dual to a two-dimensional membrane A twiddle, which is denoted in this figure. So A is not zero in this link, and it would be dual to a two-cell square, which is red. A closed two-chain dA is dual to a closed 1D flux lines partial A twiddle. So this dA is non-zero on united on this placket, and it would be dual to one cell red line passing through this placket. So this cup product term A cup dA is actually dual to the intersection between this 2D membrane A twiddle and shifted 1D flux line partial A twiddle prime. This partial A twiddle prime is the partial A shifted by negative 1/2, 1/2, 1/2. So A cup dA is non-zero if you have length here and a placket here, evaluating both to non-zero values. So I draw the dual two cells and one cells here. If I shift this length by 1/2, 1/2, 1/2, I have this blue length here. And so I see that the intersection between this blue length and the red placket is dual to the cup product of A cup dA. So I will make use of some facts in linking numbers, which is that if you imagine the case when this 1D flux lines is just a collection of non-intersecting loops, so each of them can be, they are not intersecting any vertex, they are just lines floating in space. And this A twiddle are the cyber surfaces of these loops, such that the boundary of this cyber surface gives you the collection of these loops. And there is a useful fact that if you count the intersection between the cyber surface of not I, Si, with not Kj prime, where again Kj prime is the not Kj shifted by -1, -1, -1. If sum over those intersections with a suitably chosen sign depending on the orientation, it is the same as the linking number between the two knots. For example, in this case, if I have two linking knots, then the Kj prime in this blue dot intersects the cyber surface, which is a disk for Ki in this case, and that's at this point P. And, in the case where both I and J are the same, and the intersection between Ki and the shifted Ki prime, the linking number between these two knots gives you the self-linking numbers, and the two knots intersect at a point P, which is equal to 1, because the self-linking number is 1. So we could put this formula into the evaluation of the ground-state function. So it was A dA before, and now we just use this formula because A dA is equal to the sum over the sign of intersections weighted by Qi, Qj. Using this formula, we can express the sum of sign intersection by its linking number by Kj prime, sum over pair, sum over lengths, sum over knots I and J. There are two types of terms. If I, J are different, or when I, J are the same, we shall separately write out these two terms here. If I, J are different, then this gives a linking number of distinct knots weighted by n over n. If I, J are the same, that gives you the self-linking number weighted by n over 2n. There's also a third way to express this linking number, which is counting the sign crossings when you view it from the vector 1/2, 1/2, 1/2. So if you take a knot configuration and move your camera angle to view this knot from 1/2, 1/2, 1/2, the knot knots could cross in a positive way, such as the following. And for each crossing, you put a positive sign here, 1 here. If you sum over those crossings, this will also give you a count of the linking number. So the formula written here can also be expressed as the sum over the crossings, the sign crossings weighted by Q by Qj. So the caveat is that what happens if those loops do not actually form distinct knots? Sometimes this loop will join into a vertex, and we need to give some interpretation. The interpretation is that when you join into a vertex, it doesn't contribute anything to the wave function from this vertex. So I'll just try to resolve this vertex so that there's no crossing value from 1/2, 1/2, 1/2. Once I do the reservation, and then I could do the linking formula counting to the function formula. Now I could come back to the extra term mentioned before. For odd n, there is this extra term here, which is a higher cut product, cut 1. So it has a geometric integration of the following. dA, as mentioned before, is a 2 form, which is due to a 1 cell. So if I take the triangulation before and I write down the dual lattice here, each dA is due to a 1 cell that lives on this length here. So each dA can now be resolved into a quotient part and a remainder part. By remainder part, I mean this quantity here. And the quotient part, I mean this quantity here. The notation essentially means it's a quotient when you divide by n. So say dA, if dA is 3, n is 2, and the quotient is 1 here, and the remainder is 1 here. So 3 divided by 2, the closest integer is 1. Once you resolve each dA into 2 lines, and you push the quotient lines a bit closer towards the center of the cube, then there will be some intersection between the quotient lines and the remainder lines. This term is telling you to count those intersections between the quotient lines and the remainder lines. So a final comment on to get back to what I left off before. When we're trying to solve these equations, omega 4 is d phi 3, delta alpha phi 3 is d phi 2, why do solutions exist when alpha equal to dh? So the answer is the following. Actually, you could write down a solution quite straightforwardly by using omega 4, but replacing one of the vertices by a virtual vertex. So actually phi 3, 1, 2, 3, 4, be chosen to be omega 4 with a virtual vertex 0 star, such that the length conversion from the 0 star to anybody else is 0. And similarly, for phi 2, you could write it as in terms of the cocycle omega 4 by replacing 2 vertices by a virtual index, by a virtual vertex. So this 1 star vertex essentially encodes the 1 symmetry H here into the length configurations, where we set A of 1 star I to be minus of which I. So we see that this quantity 1 star 1, 2, 3, 4, if omega 4 evaluated on this pentatron is the same as phi 3 evaluated on the modified, updated length configuration, because the left-hand side would be represented by this figure here, where 1 star is a virtual vertex. The length variables, the lengths relating I star to all the other side are given by h minus hi. The right-hand side, the length configuration on the spatial manifold is a plus dh, and on the lengths linking to the virtual vertex is 0. These two diagrams are related by 1 symmetry transformation, so they actually give you the same value. So the equation we are trying to solve here essentially translates to a cocycle condition for the omega 4, because when you evaluate d omega 4 on 0 star 0, 1, 2, 3, 4, you will get this formula. So if you omit 0 star, you get omega 4, and if you omit any of the other 5, you get d phi 3. Similarly, if you evaluate d omega 4 on this 6 vertex simplex 0 star 1 star 1, 2, 3, 4, you will obtain the formula we have here. Delta alpha phi 3 is d phi 2. It's common here that we could push further and define more quantities, which essentially encodes an anomaly in lower and lower dimensional spaces. And this is actually restatement of the work by Dominic and Naya. they are you could encode the co-cycle in symmetry and anomaly in low-dimensional spaces on the boundary. So almost ending talk, tell you about some future directions. So far I only studied the gap boundaries. What happens to the gapless boundaries?
Actually, I have a question.
Yes.
So for the 3+1D, one SPT is there. The Z2-1 symmetry, you have a full class, right? And just make sure the fate. So you construct the 2+1D gap boundary. And I think for the odd case in the Z4 class, the one symmetry will need to be spontaneous broken.
Yes.
But for the even case, does it need to be spontaneous? It doesn't.
It doesn't. It could be gapless actually. Actually, it's very nice that you mentioned this because for the angular one case, the work by UN in this paper actually mapped the boundary of this angular two case exactly to a fermion model. But with one caveat, the fermion model must have be orbifolded by fermion parity. So actually, this torical boundary corresponds to the fermion model and the following. You have orbital fermion, and you have occupied ground state, but you have four boundary conditions: periodic, and periodic. So four boundary conditions correspond to the four degenerate ground states. You have gap ground state. But if you could consider gapless fermions as well. So in that case, you could have a gapless boundary for this one symmetry.
I say even for the gap boundary, the one symmetry for the even case, n equal to 2 in your case, this one symmetry can be preserved. Is that true?
Preserve the gap. How can you count this?
This is for 3D and 2D boundary. In that case, it's always broken on the boundary.
A 3+1D both, 2+1D both.
Yes, it's always broken on the boundary. In any 2D system, one form symmetry, if it's gapped, it's spontaneously broken.
Okay.
The gapless boundaries I'd like to explore. And also, discuss about the one SPT. I could also gauge it to get a two-gauge theory where the variable live on saccades. We also think about the boundary of what could happen to this boundary of the two-gauge theory. And since we get the linking number, we might be interested to think about maybe how to get some ground state that equals other non-invariants. In general, we know that the other non-invariants have a sign relation relating 3 terms. In our case, we only relate 2 terms, so we might need to take care of how to incorporate 3 terms together. And some recent development is that it's also possible to consider non-abelian group in higher symmetry. And it's related to what Shotgun called algebraic higher symmetry that satisfy the relation that we have. If we have 2 higher symmetry acting on the same membrane, it actually evaluates to a sum of higher symmetries acting on the same membrane. Whereas in our case previously, when you add 2 of them together on the same membrane, it always gives you just one operator at the end. So actually, I'm not sure that these are all related. So that's the end of the talk. Thank you for your attention.
So, next talk. Any questions? No one.
Maybe I'll comment. So once you gauge these 2 group theories, you get to invoke a lot of things like electric magnetic duality. Recently, I showed that all of the 2 group gauge theories are equivalent either to just a theory with a fermion or an ordinary Dirac-Whitten theory. So I think point 2 is basically now reduced to stuff that's already in the literature about those things boundaries.
We can invite Ryan to speak.
I invite you to read my paper.
Newest paper you posted.
Yeah,
Yes.
recently.
It was trying to solve some of these questions that you asked about, like when the symmetry can be preserved in a gap boundary. Or
for 2, it's known that it's torical for the index 2 for Z2. But for index 1, I think Shogang showed that when you gauge it and you evaluate the partition function, it's always 1.
What do you mean index 1?
He has a Z4 classification for SPT.
Uh-huh.
But for 1, when you gauge it and you put it on any,
Oh yeah, that theory, well, it's more complicated than that because it's 0 if the manifold's not spin. Like it's a delta function of W2, so it like CP2 has 0 partition function, but like, yeah, any spin manifold.
no, but for the index 1 and Z4. That one.
You mean the
The one
generator?
with the semion boundary.
Oh, that one is proportional to the signature.
So you have to put on.
That's a Walker-Wang model, so it's proportional to the signature. So on the boundary, you would get like something that has to be chiral, unit chiral central charge. Yeah, like level 4 boundary of that theory. Is it true? Sorry, you on level 2.
What's the main claim again? Maybe Ryan can advertise. So you say
The main claim is if you want to study gauge theories rather than SPTs, it's a lot simpler. Because, for instance, suppose you just have some one-form symmetry. Okay, that's its own thing. But now you gauge it. Now there's a Z2, a two-form gauge field. The two-form gauge field, its fundamental excitations are electrically charged strings and magnetically charged particles. You can think of it instead as one-form gauge theory with electrically charged particles and magnetically charged strings. And it turns out you can do that for every single two group. It's just you have to work out what's the fate of the Postnikov classes, all the topological terms and things like that. But it eventually all works out. You can re-express everything in terms of one-form gauge theory. So the boundaries are basically already known for the case of the gauge theories. But then if you're interested in boundaries of the SPT, you want specific boundaries, right? They only correspond to certain boundary conditions of the gauge theory.
So you study 3 plus 1 gauge theory for possible 4 plus 1 higher SPT or
So
SCT.
What I showed was that the 3 plus 1D theories have a canonical form. So that constrains both what their boundaries can be and when they can be the boundary of a 4 plus 1D thing.
So you also relate some of the theory, gauge theory, to what the Lan and the Wen study.
Yeah, so they basically say something similar, but from a different point of view, thinking about how you can try to condense all the particles at the boundary of this 3D order, and that gives another canonical form of the theory, and I just showed how to get that from the bullet gauge theory. So it agrees with their conjecture, whereas before it wasn't obvious how the two group gauge theories fit into their picture, but now it is. It's too bad I wanted to find one that wasn't, but so it goes.
Yeah, maybe we can ask you to speak. Any more comments?
I also want to complain that many of the lattice constructions that you talked about in the beginning were already in my paper with Anton from like 2013. And we did one-form symmetries, we did 2 groups.
Most for the maybe partition function.
No, we did the wave function, the exact same construction here, the Hamiltonian, that's all there, boundary, symmetry action.
Also, maybe your paper was Kurt. Does it have
That was about a more, yes, something more, like more technical point. Try to understand these anomalies that seemed like they couldn't be matched by an SPT. Like they didn't have anomaly inflow. There's still some mysteries there, but
Thanks for the comments. All right, thanks. Lokman again.